Hello everyone, we are from group 6. I'm Nikta Kanchara. We are presenting video presentation 4. My team members are Yugandhar Reddy Vangala along with Venkatayappa Reddy. We are going to represent about two papers. One is a learning real-time A-star path planner for unmanned vehicle target sensing by Jason K. Howlett, Timothy W. McLean, Michael A. Goodrich, and other one is KNN LRTA star simple subgoaling for real-time search star by Vadim Boletko and Johnson. I'm going to explain about learning real-time digital path planner for unmanned vehicle target sensing. Each one. Coming to the introduction, here planning paths is a critical function of mobile autonomous vehicles. The path planning issue is especially challenging for autonomous fixed-wing aircraft because of aircraft dynamic constraints such as its minimum turning radius must be addressed throughout the path planning process. Here, aerial detection of ground-based objects complicates the challenge further by requiring a downward-looking sensor's footprint to pass over a collection of targets. Not only must the route planning procedure take aircraft dynamics into account, but also the movement of the sensor footprint as the aircraft follows a predetermined course. If the objectives are far apart in relation to the vehicle's minimum turning radius, the path planning strategy is easy. When objectives are close together, however, typical route planning algorithms are inadequate for efficiently using the vehicle sensor footprint. Next one, here the problems we are going to explain are semantic of three target sensing problem. One of yeah, the purpose of this study is to build a path planning system for detecting a collection of objects in close proximity that fully exploits the planning freedom given by the sensor footprint while functioning within the aircraft's dynamic restrictions. The purpose of route planning is to reduce the length of the path necessary to observe all of the objects. This issue is shown in the figure in the PPT, which has three targets. Here, three technological obstacles must be addressed when tackling problems of this nature, coupling between route segments using the sensor footprint and determining the viewing order of the targets. Each of this will be examined. Next one. The other problem is a coupling between path segments. A common method to path planning is to choose path segments that are the most direct route between 2 points. Here, when numerous objects are involved, the strategy entails creating an ideal route from the beginning position to the first agent, then from the first target to the second target, and until all targets are visited. When targets are widely dispersed in relation to the vehicle's turning capabilities, this strategy works well if the ideal visit sequence can be determined. When objects are closely separated, coupling between route segments owing to the vehicle's dynamic limits might result in a suboptimal composite path. The detrimental consequence of this connection is we can see that in the figure A, which is a point-to-point optimal path plan, where an ideal approach to the first objective is designed. The vehicle's direction as it flies over the first target puts it in an unfavorable position for seeing the second target. Between the second and third portions of route, a similar connection arises, while segments 2 and 3 are likewise optimal in terms of beginning position, direction, and end position. The composite route is unambiguously the best multi-target route is we can see in the second figure, which is a optimal multi-target path plan. The next one is a path shortening benefit of properly utilizes sensor footprint. Here, the majority of route planning techniques generates pathways that pass directly over the desired objects. These techniques impose overreach requirements. Numerous downwarding facing sensors used by UAVs have large sensor footprints because seeing a target does not generally involve flying directly over it. The direct flyover remains imposed by the majority of route planners do not take use of the sensor footprints, range, and flexibility. Here, the figures A and B are demonstrating the advantage of being able to use the sensor footprint while seeing objects that are closely spaced. While having a sensor with a large footprint is advantageous, employing it uh, significantly complicates route planning. Finally, when seeing objects in close proximity, determining the viewing order is a hurdle. The challenge of selecting the viewing order is analogous to the well known NP hard traveling salesman problem. Along with setting the viewing order, the route planning difficulties covered here are complicated by the restricted turn radius and an exploitable sensor footprint. The route planning strategy that is useful for seeing objects that are closely separated from a UAV needs the following capabilities, which is determines optimum or near optimal pathways between many objectives by overcoming the effects of path segment coupling, views targets entirely inside the sensor footprint, obviating the need to fly directly over them, determines the viewing order of targets that result in the shortest pathways. Here, a route planner that fits this technological criteria and approximate optimum pathways has been built using a unique version of the learning real-time A-star search. For decades, researchers have been studying vehicle and mobile robot trajectory planning. A lot of early work in optimum control was done for aircraft systems. Here, the path planning for robotic systems have received a lot of attention, leading to several methodologies being developed. This work takes inspiration from a variety of path planning methods. Devin shows that the minimum length curvature constraint route between two points have a turn, a straight segment, and a turn. And Ang and Kapila treat the topic of multiple target route planning as a parameter optimization problem. Their method keeps the vehicle's dynamic restrictions and tactical constraints in mind. The study of potential phase inspired path planning strategies. These strategies may give decent results, but they are flawed and so do not fully solve the path planning issue. Here, McLean and Bird propose a potential force based technique for UAV route planning. Frajoli et al. Devise a real-time randomized path planning method that respect vehicle dynamics, but the algorithm only evaluates one route. This method might be used to design a journey that visits numerous destinations. Random trees are related to probability roadmaps. A tree of dynamically viable nodes may be built by picking random search space point. The tree grows to the desired state. An open loop control input sequence to travel from the start node to the destination node may be discovered by tracking the needed control inputs. Ravel and Kuffner improved the RT algorithm to boost search speed. Restec has addressed route planning for UAV sensor systems. This study model pathways that keep a fixed wing UAV in line of sight with a ground-based target. The focus is on UAV route planning, not camera gimbal control. Aircraft path planning methods employing MILP have been developed. MILP approaches can provide collision-free pathways between beginning and ending states, but they need specialist software to optimize. Much work has gone into improving the speed and efficiency of real-time search. VSSA summarizes the literature on real-time search and learning real-time A-star algorithm. Next one, describe step paths. Here, path planning algorithm should provide a path that is not bound by endpoints or directions, that makes full use of the sensors brought the vehicle and that fulfills the vehicle's dynamic limitations. These capabilities may be achieved via the use of discrete step route, which are constructed by joining simple turn and stride segment to create a flyable path, the decision of which primitive to utilize at each step is motivated by a set of particular route goals, such as detecting a group of targets. Next one, the technical problems here is one is a primitive turn and stride segments assembled to form a tree of flyable paths. Here, each basic segment of a discrete step route is either a turn made at the vehicle's minimum turning radius or at a straight line. Normalizing ds by rt is the greatest heading change at each step, where it is equal to ds by rt. The number of steps in a route of given by n is equal to uh, given by the formula n is equal to pn by p, where pn is a normalized path length and pn is equal to p by rt as demonstrated in the figure. The left, right, and straight primitives combine to form a flyable root tree. The path tree has a parent node A and a child node C. Each node also keeps track of the predecessor's targets represented by the set S. T stand for known targets here. In the figure, it shows a three depth root trees. Shorter step length boost root trees resolution, while deeper trees enable longer pathways, increasing tree coverage area. Because the number of nodes in a tree rises exponentially with the tree depth, the computer memory constraints impose realistic restrictions on tree depth. Because the step length and the tree depth impact the speed of the route planning, tree search, and the quality of the resultant path plan, their function will be explored. The simplest tree building method is to produce a fixed depth tree that uses the computer's memory resources. For modern desktop computers, tree depths of 30 to 50 may be accomplished. Yeah, as demonstrated, the left, right, and straight primitives combine to form a flyable root tree. Next one, our notation for the path planning problem. Here, the vehicle's location and attitude are specified using normal aviation notation. The configuration of a vehicle at a node is defined by the triplet P is equal to xy, where xy denote the vehicle's inertial location and y denotes a vehicle direction related to north. The vector di denotes the path taken by the vehicle to reach the destination. Next one, geometry of nodes in the path tree. The vehicle detects targets anytime they enter the sensor footprint of the vehicle. The technique given here is capable of accommodating sensor footprint of any size of phone. The sensor footprint for this work is rectangular with the dimensions where X sensor is equal to 1 point RT and Y sensor is 0.5 RT, and its center is precisely the vehicle underneath the vehicle. A to decrease computing complexity, the discrete step pathway described and realized are confined to two dimensions. The methods of creating and searching discrete step root trees, as discussed later, may easily be extended to three dimensions. Next one is going to explain my teammate Hayappa Reddy.
Hey, hi everyone. I'm Venkatayappa Reddy. I'm going to discuss about LRTA star tree search. The LRTA star method is well-known method. However, it is usually used to solve path planning issues in the grid-based environments. The LRTA star method may be used to create any sort of environment, including grids, trees, discrete graphs, and more. The LRTA star algorithm is faster than A star algorithm because of the limiting factor on the performance of the path planner. Each node has a heuristic estimate h of the remaining distance to accomplish the unfinished goals. Here the HC is the child heuristic estimate, FC is the estimated remaining travel distance, and FC is the and KC is the cost of moving to respective child. The such proceeds down the tree until all objectives are met or path grows longer than the current optional path. At the time search returns to the root node. The current node's heuristic value is updated with the better estimate of the distance to the objective at each stage of the search. After the certain number of iterations, the revised heuristic converts to the real path lens. The path planner is the memory space required to store the expanded nodes. The heuristic value of the current node is updated with a better estimate of distance to the objective at each step of search and new heuristic coverage to the real path lens after certain number of iterations. Coming to next slide, algorithms. The LRTA tree search algorithms is outlined in algorithm 1, where delta H total is the total heuristic change for the current run. Count is the length of the current path, and here the best count is the length of the best path found so far, and all sense indicates whether all targets have been sensed. Moving back up the tree to the node's parent and continuing to the search from there as a class A search is possible, but it will result in significant chunks of the tree being examined without discovering a better path. Instead of sticking on one location, the search may now explore multiple area of tree to discover a better path. Coming to next slide. Initial heuristic. The initial requirement of LRTA search is that h of hi less than or equals to hi star is always true for any node of I. Reason: if a node on the optimal path overestimates the distance to the target, the search may never reach that node, and so the best path may never be found. The initial requirement of LRTA star search is that hi less than or equals to hi star is always true for any node, as been said, because it is hard to know when this will be achievable. The estimate shown on the right of the picture is utilized and first heuristic value is computed as shown below. The starting heuristic values are guaranteed to be acceptable, but they aren't always choose to real path lengths. Thus, the search may be long time to complete. An alternative The alternate beginning heuristic value is calculated the distance to the target nearest to the vehicle and add the distance to the target farthest from the first target. Because of all path tree discrete character, the step size is deducted from the first segment and the double the size is subtracted from the second segment to be conservative. The heuristic result is h equals to minimum. Here the TJ are the vectors from the nearest targets to the other targets. Yep. Coming to the next slide, terminal conditions. The strategy utilized to the end of the tree search has direct impact on the tree search speed and path length performance. On one extreme, the search continues until the heuristic change is 0. The strategy utilized to the end of the tree search has direct impact on the tree search speed and path length performance. On the other hand, the search continues until the maximum runtime is reached, ensuring that the search is completed within the specified amount of time, but with the resultant path being far from the ideal. This condition is used to end the search after the certain number of iterations have passed with no progress in the path length. Because of the best path is often located soon as and Most of the search time is spent validating that is optimum. The NIL star method finishes when path length does not improve, but LRTA star algorithm terminates when heuristic estimate does not increase. The above figure shows sample paths generated by LRTA and NIL RTA star algorithm for the same test conditions. Coming to the branch terminals, memory management and path tree trimming are critical for LRTA star tree search to operate well. The current node is terminated by removing the children and setting its heuristic value to infinity. When the when the presently examined branch grows longer than the current optimal path, and the search is resumed at the root node, as shown in the figure. If all nodes children have infinity heuristic values, the node is dead end and may be terminated similarly. The heuristic may also use it to cut uh, cut nodes from the tree, because heuristic value of a node is always less than or equal to actual path length. At the given node, h plus count ds is greater than best count ds, where count is the current depth in the tree and the best count is the number of nodes in the currently known as the best path. Then all paths are extended from the node are longer than the best path. The current nodes and all the children can be terminated safely. From a discrete step path, discrete step path tree, the LRTS star tree search is guaranteed to identify the shortest path. The genuine global optimum would be found if the step size in the LRTA tree search was reduced to infinity value. Unfortunately, because of the tree size will be too huge to search properly, this is not achievable in the practice. The findings reveal that when closing a step size, a trade-off must be made between the speed and path length performance, and the bigger step sizes are considerably enhanced to the algorithm's running time with only tiny increase in path lengths. Adapting the step size based on the number of targets is close should always for more efficient searching of bigger reasons. Coming to the next slide, testing and comparison. A collection of 2000 targets situated situation produced from 2RT by 2RT world was used to evaluate the LRTS star and NIL RTS star algorithm. 3 random pick targets were included in each scenario, as well as random starting point and heading for the vehicle. The discrete step path 3-step size has a discrete impact on the LRTA star tree search algorithms, running time and path length performance. Raising the step size, decreasing the algorithm's running time while just slightly increasing the length of the resultant paths. Coming to the next slide. LRTA tree search validation. LRTA search paths for the pinpoint and large scenarios footstep were shown below. A comparison was done between the path obtained by the LRTA algorithm and path identified using global search based Dubin's pathways to highlight the benefits of LRTA research. From figure 1, plot A illustrated that LRTA research yields a minimum length path that is almost identical to the brute force global search, with LRTA path being only 0.5% longer. The route from the figure plot 1B was created by resulting the sensor to its original size. The path is 33% shorter than path that must travel directly over the targets, demonstrating the potential of LRTA star tree search algorithm to use a whole sensor footprint while also learning the target viewing order. Coming to the path length, from the above figure shows the path length performance of the two methods at various step sizes over a spectrum of step sizes The mean path length rises by 19% round, demonstrating the smaller step sizes are preferable. The increase in main path length between zero point 0.2 and zero point 0.4 radius is just 6.8%, demonstrating the decreasing benefits of smaller step sizes. The, the picture also demonstrated NLRTA star algorithm means path length performance is equivalent to that of LRTA method. NILRTA star algorithm lengths are 3.8% longer than LRTA star path lengths at, at d equals to zero point 0.2 radians. Coming to running times. Running times for the algorithms are described by number of nodes visited by the search to display running time statistics in platform independent manner. This is not the same as number of enlarged nodes in the path tree, but rather the total number of moves performed from the node to node through the tree search. The average overall running times for both algorithms at various step sizes are plotted in the above figure for LRTA star and NI LRTA star algorithms. From the above figures, the results shown in the plot B are mean running times at which the best paths are found. Approximately 85% of overall running time of LRTA star algorithm is spent validating the best path. Yep. Coming to the next slide. Different number of targets. All the data shown in the so far were acquired using three target situations. 2000 random target situations are utilized for each number of targets between 1 and 8 using 0.25 gradient step size for testing assess of algorithm performance for varying number of targets. The effect of increasing target numbers on running time and path length. From the above figures, the running time of both LRTA star and NI LRTA star algorithms increases with number of targets. The LRTA star algorithm visits an average of 5.5 million nodes for 8 targets compared to the average of 200,000 nodes for NI LRTA star method for 5 seconds. For any number of targets, the NILRTA method is consequently quicker than LRTA star algorithm, and its path length performance is comparable to LRTA star approach as shown in plot B. Coming to the conclusion, the LRTA star and NILRTA star research algorithms are located at the branch from the discrete step root tree that best achieves a set of specified objectives. The LRTA star algorithms will always generate the shortest paths, but it will take longer to run. The NLIRTA star algorithm succeeds in satisfying some paths length performance in exchange for sustainability quicker running times. By overcoming the consequences of path segments coupling, the LRTA star and NLRTA star algorithms plan optimum or near optimal pathways via many targets. They make full use of sensor footprint to examine targets and avoid flying straight over them. As part of the planning process, they also establish the best viewing sequence. Both algorithms give solutions to numerous closely spaced target sensing problems, as well as flexibility to increase the range of goals and limitations in the fashioning. Yeah.
Thank you, Nikita and Ayappa, for explaining the learning real-time A-star path paper clearly. I am Yugender Reddy Vangala, going to explain about KNN LRTS star algorithm, a simple subgoaling for a real-time search algorithm method by Vandim and NV. The paper is about to develop a new high-performance real-time search algorithm suitable for path finding in different kinds of video games. We'll start with the abstract. The heuristic chase computations satisfy a consistent bound on how much orchestrating per action liberating from issues size. The real-time heuristic pursuit estimates would make them suitable for PC games where artificial intelligence controlled experts out to answer quickly to client orders and to the other experts. The DLRTS star method endeavors to dispose of advancing through ordinarily picking subgoals. DLRTS star is for the most part around ready for PC games. Adjacent to it has a complex and memory referencing pre-assessment stage during which it assembles an information base of subgoals. In this paper, we propose a less complex and more memory valuable system for prefiguring subgoals, thusly swearing off the fundamental hindrance of applying top-level advancing sophistication strategies in the PC games. The real-time search algorithms explain using the different phases, the vital study or the vital study heuristic pursuit estimation to do this intent to speed up learning process by DLRTS star algorithm. The DLRTS star had a huge memory necessities and a complex pre-taking care of module. DLRTS star separates a state, space, and cycles. Coming to the sub-goal database constructions, you can see on the screen how a system-based map is changed over to a chart, which is 10 detached, so every group of one of kind states transforms into a single hypothetical state. At the point when the reflection is done, a ground level state closer to the centroid of the click is picked as a specialistic for the hypothetical state. The specialists are separate with minimal white circles partially. DLRTS star code is insignificant as the need might to manufacture the club pondering, find ground level specialist and then run Dikshitra 2 method from the start specialist contrasting with separate goal state and follow the way from the ground level specialist constructing with the hypothetical starting state. You can see in the screen the different how the shapes are changed from first to the fourth one. Coming to KNN LRTS star algorithm method, it is the most clear and fastest type of progressing pursuit. This method is explained in the picture using the example of hill climb. The runtime search algorithm enlists a sub-goal for each pair of states. The heuristic distance on map is typically a procedurally resolved limit. For instance, distance, Manhattan distance, or the optical distance. These distances dismiss the map impediments whenever the expert observes the informational index record commonly practically identical to its current situation. It sets the sub-goal from the record very much like own sub-goal and go on towards it using the standard LRTS star algorithm method. In this, in the first place, the overall goal may be slant climb being reachable from the expert's current status. However, the expert could pick a sub-goal, pushing it away from the goal. We address this by expecting the overall goal is slant, climb being reachable from the expert's current status. Expecting this in the situation, then we head for the overall goal and the sub-goal assurance completely. Second, though the sub-goal is by improvement incline climbing reachable from the start, it isn't actually from the expert's genuine state. Along these lines, the expert could run into the obstacles enduring to show up at it. The third issue lies with expecting cycles. It can so happen that the expert shows up at its picked sub-goal and a short time later sets. Following the coming to the sub-goal, it could end up picking sub-goal again along these lines, entering a boundless circuits. Coming to the fourth one, in light of the fact that our similarity metric relies upon octile distance, it disgrades obstacles. In this manner, the most similar record could contribute a lot of energy working its way around the obstacles. And then coming to the properties of algorithm, the path satisfies the consistent prerequisite. We will show that the last choice satisfies the continuous limit so much as the amount of CPU time taken doesn't increase with the map size. The KNLRTA star is also completed in light of way that it finds its level headed in a restricted proportion of time if the aid is restricted and the goal is arranged in a comparable related part as the expert's fundamental state. So the expert will continuously show up at its sub goal, and each sub goal can be used everything through about once. Coming to the empirical evaluation. For explaining this method, we have used 8 different aids from PC games. The map were represented with grid sizes ranging from 150 into 141 to 234 into 274 cells. On each guide, we can run 128 unmistakable path findings issue events with the start and objective regions picked randomly but obliged, so the best game plans cause of the ways were practically identical, even more unequally in the range of 100 to 150. The pathfinding computations included the octile distance as the heuristic. They were attempted with one or two definitions for DLRTS star consideration levels. The suboptical the, sub, the suboptimally is communicated as a level of amount more extravagant the ways the are than ideal ones. The graph shows the results of empirical evaluation. The two subplots in the figure shows the suboptimally of ways explored by experts obliged by either DLRTS star method or KNN-LRTS star method. The right subplot presents suboptimality as a component of the amount of states per move. DLRTS star suboptimally varies, outperforming that KNN LRTS star only for thought levels. However, DLRTS star requires over the top proportions of memory for its level 3 subgoal database. Two data centers fall outside the span plotted in the charts. DLRTS star in the left subplot and the KNN LRTS star in the right subplot. KNN LRTS star performs somewhat more lamentable than DLRTS star, while requiring through and thorough less memory for its sub-goal instructive assortments. The trade-off is appealing for pathfinding in PC games, especially on consoles where memory is routinely an insufficient resource. This is how we have explained about the game using the 8 different of PC games. Let us come to the conclusion part. The fundamental drive behind this work was to make a new world-class execution persistent request computation sensible for pathfinding in PC games by relaxing memory necessities of DLRTS star. A current status of workmanship continuous chase estimation. The new computation KNN LRTS star offers clear benefits for pathfinding applications in PC games. We acknowledge that KNN LRTS star can be, moreover, improved to totally match DLRTS star runtime execution going forward. Thank you.